Okay, so the unit of kinetics is the study of the speeds or the rate of chemical reaction. When we are dealing with this, there are two things we need to understand. We need to understand how to determine the rate at which the reaction occurs, or the speed, and we need to understand any factors that control this, like activation energy or concentration. We'll talk about the factors in a minute. Because sometimes a rate of reaction, how fast a reaction is going to occur, really depends on the characteristics of the reactant. Because we need them to be able to react, and they need to have certain characteristics. So we're looking for two things. We're looking to determine how fast a reaction occurs, which is its rate, and we're looking to look at the factors that help determine how fast a reaction occurs. All right, those are the two things we need to understand. So we're going to spend a few minutes talking about the factors that control the rates of reaction. All right, think about it like this, okay? Every car could get up to 60 miles per hour, okay? But it depends on the kind of car that you have as to how fast you will get there, all right? Whether you have, you know, a smart car, or whether you have a Porsche 911 that's midnight blue with whale tail.
What is the car?
That is my dream car. All right.
Keep that in mind.
Yeah, Christmas is coming, you know.
Yeah, I want to spend,
How much is your AP chemistry grade worth to you? Okay.
What about the way?
Ooh, I don't know. Well, killed deal breaker. Okay, so.
I don't think being your teacher is going to help you.
You can have a 97
I'm good with my Beamer, so.
It takes a little bit to get
But you guys get the idea. Every car can get there. Every car, well, not every car. Most cars can get there. It's just a question of how fast you get there, and it's about the performance of your car to get you there. Okay, that's the kind of thing I want you guys to think about. Okay, so we are talking about factors that affect the rate of the reaction. Okay, because reactions involve the breaking and the forming of bonds, because that's all a chemical reaction is. You break the bonds of the reactants, you form bonds in the product. All right. The speed depends on the nature of your reactants, just like it depends on the nature of your car. Okay? It's all about the frequency of the collisions between the molecules, how fast those molecules are moving, and they make collisions. And those collisions are what break and form bonds, is those collisions between the reactants. Because the two reactants have to get together in order to break the bonds in the reactants and then reform the bonds in the product. So, the more collisions that you have between your reactants, then the faster the reaction goes. So these are the four factors that affect how quickly a reaction can occur, meaning how it can have more collisions. All right, the first one is the state of your reactant. Okay? Which state is going to be the most active state? The gas. Why? It moves faster. It has a higher kinetic energy in it. So it already is moving faster. Therefore, you're going to have more collisions. And therefore, rates are going to happen faster. All right, so the state of the reactant really can determine how fast a reaction occurs. Okay? Reactants in the same state are more likely to react. Reactants in different phases are limited to the area of contact, or the surface area. Okay? So that's a really important thing. So let's say, let me get my pen, and let me draw a little. All right. We've been talking about the reaction of sodium in water. Okay? So if I have a beaker of water, and I put some sodium in it. I'm going to put a little chunk of sodium. I'm making my sodium red. Alright, I'm going to put a little chunk of sodium in my water. Well, first, the sodium is actually going to stay on top of the water. Why is it going to stay on top of the water? It's not that it's less dense. They're reacting, aren't they? Okay? The water right here on the surface is reacting with the sodium atoms on the surface of the sodium. Okay? And because that reaction is producing so much energy, it actually stays on top. It's not going to fall down inside. But if it did fall down inside, okay, or if I pushed it under the water, now we have more surface area. That means more reactions. Okay? So, how can I make this react faster? I can push it down in the water, that's one way. Pour water on top, same idea. I could break it up into smaller pieces, alright? The other thing I could do, this is a metal, right? And metals are malleable, alright? And so I could take this, and instead of being this big square, I could take it and make it flatter.
Would it just sit on top still though?
Yes, but don't I have more surface area? It still will sit on top, but I'll have more surface area for the reaction to occur. Then my reaction is going to happen faster. Okay? Another analogy to this is something you guys do all the time. Okay, I'm going to draw another beaker. Let's make it green this time. And instead of my beaker being full of water, now my beaker is full of tea. Okay? Now, what do you do with tea? Well, when you first make tea, you got to add something to it because we live in Alabama. You add some sugar to it. Where does the sugar go? It goes to the bottom. Okay? So, what part of the sugar is reacting and dissolving into the water? It's just the surface, right? The sugar that's underneath isn't reacting with the tea because it's buried underneath all the other sugar molecules. So what do you do to make it dissolve faster?
Swirl it.
You stir it. And so when you're stirring it, you're putting the sugar cubes, which they're crystals, you're sending them out here. And what are you doing? You're increasing the surface area. Exactly. Okay? Or you could get it hotter, and that will cause this, it'll cause the heat, will cause it to dissolve faster too. Alright? So, the physical state of your reactants will really dictate how quickly your reaction will occur. Alright? Second thing that will happen is the concentration of your reactant. Alright? Concentration is really, really important because if you have a higher concentration, then you have more reactants available for collision. If you have a really low concentration, you don't have as many reactants available for collision. Alright? So, what happens as a reaction progresses is your collisions start slowing down because you're running out of reactants. And we'll look at a graph of that in just a few minutes. Okay? High concentration of one reactant makes the reaction easier. Third thing, temperature, and this is what we were just talking about, dissolving the sugar in your tea will make your tea hot. Don't wait till it's cold. Alright? Heat up your tea, or right after you make it, the sugar dissolves faster. Okay? And you can actually put more sugar in it because it's hot than you could when it's cold. So temperature is a huge factor. And then the last thing that's important is a catalyst. Catalysts allow for accurate collision. Okay? Now, I gave a different analogy to 2A, but I'm going to give you another idea. Y'all remember when you were a little kid? I'm talking like, you know, you're like in elementary school, and you go on the bowling field trip. Everybody went on the bowling field trip? All right? So the kindergartners are there, and the fifth graders are there. And the kindergartners have a harder time hitting the bowling pin. Because it's way down there, and they're not so big, it's harder for them to roll the bowling balls. So what do we do for the kindergartners? We put it on the stand, we put the bumpers up so that it doesn't fall into the gutter. We help them get their collisions down to the pins by giving them a way to funnel their ball down, yes? Okay? Now you're grown-ups, you shouldn't be using, well, you're not grown-ups, you're children, but, okay, you're young adults. You are not grown. You should not be using the bumpers and the gutter guards and the stands. No, they look silly. I know they help. But that is what a catalyst does for you. It helps funnel your reactants so that they have the right collision. Because, guys, if you don't have the right collision, let's say you roll your bowling ball down and you just hit the edge of the pin and the pin doesn't fall over. Your collision was ineffective, nothing changed, okay? So we want to make sure that you have effective collision, and that's the job of a catalyst. It funnels the reaction so it has a really strong collision so the reaction will take place. All right? So these are the four things that will affect the rate of a reaction. First is their state. Second is their concentration. Third is their temperature. And then finally, a catalyst. Those will help speed up reaction. Okay? Any questions on those? Because we're about to hit our first type of reaction, or reaction rate.
Would pressure be a factor?
Pressure would be a factor, only because it can affect temperature and concentration. Okay? Because pressure affects volume, and volume would affect concentration. Okay? Good observation, Jacob. Okay, so how do we calculate a rate? Well, speed is a rate. It's miles per hour, or kilometers per hour, okay, or meters per second. Well, rates of reaction are just your change in your concentration over your change in time, okay? Now, keep in mind that these brackets right here, anytime you see brackets, that means concentration, okay? So a bracket like this, and you've seen me use them, that equals concentration. What is the unit for concentration? It's molarity, which is moles per liter, okay? So we're talking molarity. That's what concentration is, all right? So your rate is calculated by the change in your concentration over the change in time. Now, keep in mind we have a little bit of a sign thing that we have to deal with. Why? Because reactants are being used and products are being formed. So what's going to happen to the concentration of a reactant? It's going to decrease because we're using it. And what's going to happen to the concentration of a product? It's going to increase. So aren't they opposite of each other? Reactants disappear, products are made, so they're opposite of each other. All right? So here's just a little diagram to show you what's going on. All right? Here at 0 seconds, we have 1 mole of A and no moles of B. At 20 seconds, we have 0.54 moles of A and 0.46 moles of B. Okay? So what happened to the rate of A? All right? Well, what happened to A? What was its final concentration? No, that was initial. Final? Well, we're going to just go to 20 seconds. So it's 0.54 minus 1
You're just doing a slope.
over, yes, we are doing a slope. over 20 seconds. Okay? So that gives me, what do I get? Negative 0.46 over 20 seconds, molar. Okay? So for that period of time, from here to here,
Would it be in moles?
it's concentration, molarity. Okay? From here to here, A went from 1 to 0.54, and it was 20 seconds. Why does it have a negative sign? Because it decreased, because the reactant is disappearing. Alright, so what's going to happen to B over that period of time? Well, B started at 0, and it went to 0.46 minus 0 over 20 seconds. So that's 0.46 molar per 20 seconds. And then you can calculate what the rate is. Okay? See the relationship? This one is negative because it's disappearing. This one is positive because it's appearing. Alright? Now there's a little caveat here. For every mole of A, how many moles of B did we make? The same amount. Okay? So for this reaction, it's A yields B. 1 mole of A yields 1 mole of B. Okay? That's not always the case, is it? As a matter of fact, that's rarely the case. So we're going to have to take that into account. Here it's a 1-to-1 molar ratio. Alright? But everybody see the fact that it's negative for disappearance, positive for appearance. Yes? Alright. So let's move to the next slide. I want to skip that one for a second. Okay, so here's my reaction. A moles of A, B moles of B, yields C moles of C, D moles of D. Okay? Now, don't look down here yet, because this is going to confuse you. Alright?
Okay.
What's the relationship between the moles of A and the moles of C? If I had 2 moles of A, let me get a pen. If I had 2 moles of A, and I wanted to calculate how many moles of C that was, what would I do? Stoichiometry.
1 mole.
It's A moles of A yields how many moles of C? C moles of C. Okay? Where did you get those numbers from, or letters from? The coefficient of the reaction. Okay? Now, these are the same, and I had 2 moles of A, how many moles of C would I get? I would get 2. But if they're not the same, then I have to take into their stoichiometric relationships, yes? Okay, so, and you'll see this, I'm about to explain this with a problem, but here is the relationship between A and C. Now, where did I get these fractions from? They're their stoichiometric relationships, okay? Because for every 1 mole of A, how many moles of C do I get? I get C over A moles of C, yes? Right here, we just did it. Alright, let me give you a problem, and this will make it, it'll make it clear once we do the problem.
And would C over A be the same as C over B? No, never mind, just kidding.
We're just in moles. Okay, let me give you a problem, and it'll be clear. Okay, so here is my reaction. What's O3? We have a hole of it in our atmosphere.
Ozone.
That's ozone, O3. Okay? Or you could have actually read and it says ozone right there. Okay? So, 2 moles of ozone degrade into 3 moles of oxygen. Okay? There's your stoichiometric relationship. Alright? So, it says, let's do their relationship. Don't read the rest of it. Let's just do their relationship. Okay? So, the rate of the disappearance of O3 over time, how does it relate to the rate of appearance of O2 over time? Well, first, this is a reactant, right?
Yeah.
So what does it need? It needs a negative because it's disappearing, all right? And so for every 1 over 2 moles of O3, I'm going to put a negative there because it's a reactant, we get 1 over 3 rate of O2, okay? Where did I get these numbers?
Coefficient.
From my coefficient, okay?
Why'd you make it 1 over 2 though? Just do it.
That's a lot of moles of O3.
You'll see. Let me rearrange and you'll see. Okay? So, here's a number. They give us the rate of appearance of O2. They tell us the number of the rate of the appearance of O2. So we know we can plug in that number right here. Alright? So we can say negative 1/2 the change in ozone over time is equal to 1/3, alright, 6 times 10 to the negative 5 molar per second. Okay, don't grab your calculators. Let's rearrange. What's the question asking me for?
The rate of O3.
I want to find this. Alright, so what do I have to do to get this by itself?
Multiply by 6 by -2.
I've got to move this over here, right? So I can say this is equal to negative 2/3 6 times 10 to the negative 5 molars per second. Alright? How does this number, where does this number come from? Okay? It's these numbers in a relationship, right? Okay? This ratio to this ratio, for every 2 moles of this, I get 3 moles of this. Okay? So that's where this fraction comes into play. It's the relationship between this and this. Now, without your calculator, could you do this math? You should be able to. Alright, what's 2 times 6? 12 divided by 3 is 4. 4, don't forget this part, it would be negative 4 times 10 to the negative 5 molar per second. Does that make sense? Is the rate of disappearance supposed to be smaller than the rate of appearance? What are we making more of? We're making more O2. So this is going to show up faster. Why? Because it's got 3. For every 2 moles of this, I make 3 moles of this. So essentially, for every 1 mole of this, I make 1.5 moles of this. So isn't this going to appear faster? Does that make sense? Okay. Y'all are going to practice with this in your homework assignment. Alright. Let me go back 1 slide. 2 slides, I think, actually. And talk about this last thing. Okay? What if I want to find a point on a specific graph? Okay? This is the other way you can calculate rates. is over a small period of time. This is a graph of the concentration of this versus time. All right, is this a reactant or a product?
It's reactive.
No. Yeah.
Yeah, it's reactive.
It's a reactant,
Yeah.
okay? And look at its concentration. It's going down. Does that make sense? Yes, because we're using the reactant. Now, why is this a curve and not a straight line?
Because it gets slower.
As you go down the reactive, the reaction slows down.
As the concentration of my reactant starts getting smaller, my reactions are slowing down. Why are my reactions slowing down?
There's less concentration.
There's less concentration,
There's
which
less
means
collisions.
fewer collisions. Okay? So, the data that I have here gives me this curve. But what if I want to find a point? I want to find the rate at a specific point in the reaction. Alright? I want to find the rate at 600 seconds. There's the spot for 600 seconds. I don't have data for 600 seconds. So, here's a math idea. We very rarely have to do this, but every once in a while we do. If I want to find a point on a curve, then I'm going to use the line tangent to that curve, okay, and find the rate there, okay? Can you use your calculator to do this? Yes, you can. All right?
Just do some math.
Okay? All right, so, homework. Listen up. Homework assignment. You have 5 problems from the book. 2 of them you need to use your graphing calculators for. All right? So make sure you're comfortable with your graphing calculator. If you need to check out a graphing calculator, come and talk to me during break. It's at the end of chapter 18, I think it is. Something like that. The kinetics chapter, whatever it is. It's just 4 problems. We'll go over them on Thursday. There's a Tuesday topic for the day after school. We finished up net ionics. So if you didn't come this morning, come this afternoon. You have a midterm coming up. All right. Your midterm.
Believe in yourself.